I greet you wherever you are watching this video all over the world, learners of chemistry, my chemistry students. Okay, I am your chemistry tutor, Mr. Akweji Honesty. This is a topic before us, rate law and rate constant. Okay, whenever you write a rate law, the constant that is associated with it becomes the rate constant. Okay, if you have a reaction like this, A plus BB to give you CC plus DD. Okay, this is counted as reactants. These are counted as product. Okay, there is a law called the law of mass action. The law of mass action, okay, actually states that the rate of reaction is proportional to the product of masses or concentration of the reacting species raised to the appropriate power. Okay, and the power is equivalent to the coefficient that occur in the chemical reaction. Okay, what the law of mass action is saying is that rate, okay, is proportional to the concentration of the reactant. Please note this. This raised to the appropriate power. Okay, this is what the law of mass action is saying. Okay, that rate is proportional to the concentration of the reactant raised to the appropriate power. This power signifies the coefficient, okay, of the reacting species. Do you understand? So, by implication, if you write the equation, you have R, which is rate, is equal to, you'll be introducing a constant K, which is our rate constant, and that means our reactant A with respect to A, that is reactant A, then this is the coefficient of A, then it will now be raised to the power of A. Okay, the product, he said that the rate of reaction is proportional to the product of the concentration of the reactant raised to the appropriate part. So you will not put plus, you will not put minus, but rather it is a product of the concentration of the reactant A raised to the power of the coefficient A, then reactant B raised to the power of the coefficient B. Do you understand? This is the rate law for this reaction. This is the rate law for this reaction. Okay. So, for example, you have a reaction this way: hydrogen plus bromine gas to give you hydrogen bromide gas. Okay, so if you are going to write rate law for this reaction by from theoretical view, you are going to have R is, let me use this, proportional to the concentrate to the product of the concentration of the reactants, okay, raised to the appropriate power. What is the power? The power is related to the coefficient of the concentration of the reactant. Okay, and the coefficient is likely the number of moles. So you have one here. That means one will be here. Then you also have the bromine concentration of bromine raised to the appropriate power, which is the concentration of, I mean, the coefficient of bromine, which you have one. So that means you are going to have R is equal to your rate constant. Okay, you have hydrogen raised to power 1, bromine raised to power 1. Okay, this is how to write. This is the rate law for this reaction. I hope you understand. So this means concentration of hydrogen. In chemistry, you use this to represent concentration. Do you understand? So this is concentration of bromine in the reactant, and K is our rate constant. Okay, K is the rate constant, and the unit for the rate constant is not specific. It depends on the what you have in your reactant. So you do the proper ratio and you will have the proper unit, okay, you put the proper dimension, okay. This is the rate equation. We call it rate law or rate equation. So by definition, we can say that rate law, what is rate law? We can say that rate law can be defined as an empirical equation that expresses the rate of reaction as a function of concentration of all species present in the overall chemical reaction, okay, for the reaction at the same time, okay. That is what rate law is all about, okay. So whenever you write the rate law of a chemical reaction, your rate constant will also be present. But please note that the rate constant does not have a specific unit, that anytime you calculate rate constant, it must carry this particular unit. The unit depends on what you have from your rate equation, okay. For example, look at this. For example, you have, if you make K the subject of the formula here, K will be equal to what now? Rate over concentration of hydrogen, concentration of bromine, okay. And you know that rate is actually concentration over time. And if your concentration is in mole per liter, for example, then over time, which is second, that means you'll be having mole per liter per second, okay. That will be the unit for what? Rate of reaction, mole per liter per second, okay. It may not just be mole, it can be gram per liter per second, as the case may be, but here I'm working with mole. So if you have it like that, that means your rate here is mole, okay, per liter per second, divided by this one. Concentration will be what? Mole per liter times what? Mole per liter. So you need to solve this. Whatever comes out of this gives you the unit of K, okay. There are equations where you have only A to give you P, and your rate will be K, okay, the concentration of A raised to the power of 1. So if you get your K here, your K will be R over concentration of A. So you don't expect that the unit of K you will get here will be the same unit of K you are going to get here, okay. They will actually be different. So this one will be mole per liter. So you can see that you have mole per liter times 1 over second. You have mole per liter divided by second. When you remove the sign of division, it will now be times 1 over second, okay, divided by, you have mole per liter times mole per liter. Definitely, mole per liter will cancel mole per liter. So you are going to be left with, okay, per second, you have mole per liter. Let me write it here. Per second, what you have here is per second. Then mole per liter. Remember, there is still a division sign here, which is a per. Mole per liter, okay, which is this. Then this one already show is like this. Do you understand? So this is a unit, okay. It is accepted. This is a unit of this K, okay, except you want to solve further, where you are going to have mole 1 over mole per liter, then you multiply it by this, okay. So in a nutshell, this is, or you leave it simply as mole per liter per mole per liter, okay, per second. You get it? Per mole per liter per second, okay. That is the, but that is the unit of this. But in the case of this, your R is mole per liter, okay, per second. Then divided by mole per liter. So you are going to have, when mole per liter, we cancel mole per liter. See, you are going to have what now? Per second. So here, K will just be per second here. I believe you understand. Okay. So that defines rate law and rate constant. So I will want you to determine the rate law and the rate constant and the unit of the rate constant from this reaction. Okay. Do it from the understanding you already have from this video. Okay, let me give you an hint. Your rate, for rate law, rate will be equal to what? Your constant, the concentration of N2O5 raised to the power of 2. Okay? Then make K the subject of the formula and deduce the unit of K. I hope you understand. Okay, thank you for watching my video. Okay, I want you to watch more of them and share to others. Thank you. I remain your chemistry tutor, Akpeji Honesty.